Hey guys, it's Miss Johnson, and I'm here to bring you the second part of our notes for section 7.1. In the first part, we talked about what is a sampling distribution, and today we're going to talk about how we describe a sampling distribution. So that's the piece that's coming next for us. So we're getting back into that describing part where we would describe distributions before. We also described sampling distributions. So when we describe a sampling distribution, it says a statistic is used to estimate a parameter. It is called an unbiased estimator if the mean of its sampling distribution is equal to the value of the parameter being estimated. So if we took all the possible samples of 20 chips, if we go back to that 20, if we go back to the red and the blue chips where they were deciding the homework work time, if you took all possible samples of 20 chips from a population, calculated the p-hat for each sample, and then found the mean of those p-hat values, we would get exactly 0.5. Okay, that's what that statement is saying there. That's an unbiased estimator. Okay, in this question, we are going back to that Heights example where we had John and Carol with 4 sons, and we pulled sample sizes of size 2, n equaling 2, and we found the mean, and we did the sampling distribution, and then we found the range, meaning one minus the other, and did the sampling distribution. So the question here is the sample range an unbiased estimator of the population range? Explain your answer. So what makes it easy for us to look at it here is we're only looking at a population of 4, and so it's not hard for us to do the sampling distribution and to also look at the population parameter. So for the range part, our sampling distribution looked like this. We had, the dot plot where we had 1, 2, 3, 4, 5, 6, and 7, and 3, 5, 7. I'm just labeling every other for the sake of time. So we had a dot at 1, we had 2 dots at 3, we had 2 dots at 4, and we had a dot up at 7. So if I found the mean of that, if I found the mean of the sampling distribution, I would take all of those and add them up and divide by how many there are, which in this case there are 6. So I'd have 1 plus 3 plus 3 plus 4 plus 4 plus 7. And I'd divide all that by 6 and I'd get 3.67. Okay, so that's the mean of our sampling distribution. Now, if I take the actual range of the population, the range of the population is 75 minus 68. Which is 7. So the thing here is, here's our mean of our sampling distribution. Here's the actual parameter. Okay, and we know that to be true because we know the whole population. The population is only 4 people. I know their heights. I know the range of the whole population. The range of the whole population is 7. So the question is, are these two things equal? And in this case, no, they're not. So because the mean of the sampling distribution is not equal to the population parameter, is not then this is not an unbiased estimator. Hello, estimator. I could probably write that out correctly. Estimator. There we go. Okay. So it's not an unbiased estimator of the population range. Okay, so when we get into describing the sampling distribution, it says to get a trustworthy estimate of an unknown population parameter, start by using a statistic that's an unbiased estimator. So obviously, when your population is only 4, it's very easy for you to calculate those population parameters. I could do the population mean, I could do the population range, because I only have 4 people in my population. When you're talking about all US adults or even all students at Farmington High School, that would be a hard thing for us to get the actual true population. It's not easy to do. So when we can't get the true population, we need to use an unbiased estimator. We need to be careful that that is what we are selecting. But it also says, unfortunately, using an unbiased estimator doesn't guarantee that the value of your statistic will be close to the actual parameter value. It's better to use an unbiased estimator, but you don't know if that's actually going to give you the right thing. It says we prefer statistics that vary less from the actual parameter value. So larger random samples tend to produce estimates that are closer to the true population value. So that's going to come into play. We talked about that large counts rule back in chapter 6, and we are going to learn about an appropriate sample size when we start doing tests for significance. And we know that if we increase our sample size, we get closer to the population parameter. That's just a fact that we've known for a long time now. So it says in many cases, it is obvious which statistics should be used as an estimator of the population parameter. If we want to estimate a population proportion, use the sample proportion p hat. If you want to estimate a population mean, use the sample mean x bar. So remember, we go back to that theory, I think it was in chapter 3, where our statistics were hats. So when you have a sample size, you need to put a hat on your statistic or on your notation. Okay, so here we're going to talk about bias and we're going to talk about sample size. So it says to decide which estimator to use when there are several reasonable choices, consider both bias and variability. Bias means that our sample statistics do not center on the population parameter. In other words, our estimates are not accurate. High variability means that repeated samples do not give very similar results. In other words, our estimates are not very precise. So there's 2 different things going on here. You can think of this, they have a really great graphic here. You can think of this like a bullseye. So when you have an estimator, I'm going to start in this lower right-hand corner right here. This is like your money shot. When you have an estimator with no bias and low variability, you're in the bullseye. And that's what you want. You want no bias and low variability, okay? If you have an estimator with low variability, meaning the data is all clumped together, but high bias, that pushes your data out away from the center. So it's good to have low variability because your data is close together. Your statistics are precise, but high bias means that you are not near the population parameter at all. You can also have an estimator that has a low bias, meaning they're all close to the center. Here's your center. They're kind of close, not awesome, but kind of close, but they have high variability. So they're kind of all over the place. So that's not helpful either. Then the worst case scenario is you could have both. High bias and high variability. Then you've got this clump of data that's all spread out and it's away from the center. Okay, so your money shot is when you have no bias and low variability. That's really the goal here. So one tip for the AP exam, it says make sure to understand the difference between accuracy and precision. It's confusing because those 2 words are very, very close. If you look up their definitions in the dictionary, they'd be very, very close to each other. So what they say is many students use accurate when they really mean precise. For example, a response says, increasing the sample size will make an estimate more accurate. That is not correct, okay? It should say that's a no-no, okay? Increasing the sample size will not make it more accurate. What it should say is increasing the sample size will make an estimate more precise. When you increase the sample size, it makes the estimate more precise. If you can't remember which term to use, it says don't use either and just explain what you mean without using those terms. So you can go into detail of what you did with that particular question using context without having to be worried about which term is correct or not. But if you increase the sample size, then you get more precise. All right, this was short and sweet. That takes us to the end of section 7.1. So thanks for tuning in to this piece, and we will carry on with section 7.2 next time.